Steps to solve this problem. The first thing we're going to do is we are going to visualize this problem using a graph. The second thing we're going to do is we are going to write vector equations for each ship, ship A, and for ship B, that are going to give their position vector relative to the origin as a function of time. And then after we do that, we are going to set these position vectors equal to each other to see if they're going to be in the same position at the same time. Okay, so the first thing we're going to do again is we're going to visualize this information using the graph. So for the first ship, ship A, I know that its position at noon is 6, 10. So 1, 2, 4, 6. 2, 4, 6, 8, 10. So it's up here. This is ship A at noon. And I know that it's headed has a negative kind of direction, so it's headed kind of this direction. So it's going to be going something like this. All right, the other ship, I know that at 12:02, ship B is at the origin. So the first thing I need to do is I need to synchronize the times for the two ships. I need them to both have the same initial value for the time. So I'm going to use noon as my initial value. Okay, so I know the position of ship A at this initial time value, but I need to know the position of ship B at this initial time value. I know the position of ship B 2 minutes after this time, and I can use its velocity vector, which was given, to back it up 2 minutes so that I know its position at noon. So with its velocity vector, I know that its velocity vector was +7 and -3. So it went 7 forward and 3 down. So over here. So this represents the velocity vector of ship B. All right, and so then what I can do is I can use this velocity vector and back the ship up 2 times. So every 1 minute, the ship travels this distance. So at 12:01, ship B was 7 back from the origin and 3 up from the origin. To figure out its position at noon, I want to back it up one more time. And at noon, ship B was back here at -14, +6. So again, I use the velocity vector of ship B to back it up to noon. And this is its position at 12 o'clock. So now I have the initial position of both ship B at 12 o'clock and also ship A at 12 o'clock. And from there, I can make my vector equations. All right, so for ship A, I know that its position vector relative to the origin is going to be equal to its initial position vector, which is 6, 10. Plus t times its velocity vector, where t is the number of minutes after noon. All right, so I need to find its velocity vector. I'm given the direction of its velocity vector, so I know that its velocity vector is parallel to the direction vector I was given, which was -3 I hat minus 4 j hat. And I also know that the speed of ship A is 10 kilometers per hour. So the magnitude of the velocity vector is 10 kilometers per hour. So I need to find the magnitude of the direction vector, and then I need to scale it so its magnitude is equal to 10. So the magnitude of this vector is going to be 5, right? Because this is a 3, 4, 5 right triangle. So the magnitude of the given direction vector is 5. I want it to have a magnitude of 10. That means that my velocity vector is going to be 2 times my given direction vector. And now that I have a velocity vector, I can substitute it in here to my vector equation for ship A. So my vector equation for ship A becomes R sub A equal to 6, 10, the initial position, plus T times negative 6, negative 8, where T is the number of minutes, afternoon. All right, I need to do the same thing for ship B. And for ship B, I found its initial position. By backing it up 2 minutes. So I know that its initial position is negative 14, 6. That's its initial position vector from the origin. And I'm going to add t times its velocity vector, which was given to me in the problem statement. The velocity of ship B was given as the vector 7i hat minus 3j hat. And here t is reference to the same starting point. So t is the same, has the same definition that it does up here. All right, so I'm done with step 2. I have a vector equation for the position of ship B relative to the origin, t minutes, afternoon. And I also have a vector equation for the position of ship A relative to the origin, t minutes, afternoon. So what I want to do to see if they collide is I want to set these position vectors equal to each other and see if they're at the same place at the same time. So I'm going to be setting the position vector for ship A equal to the position vector for ship B. Okay, and when I do that, I'm going to do it in terms of their parametric equations. So remember that if I have this vector equation of a line, negative 6, negative 8. I remember that this, right here, I could write as the x and y displacement for ship A from the origin. For ship B, I could do the same thing. For ship B, it's going to be negative 14, 6, plus t times 7, negative 3. Okay, so when I say set these equal to each other, what I really mean is set the x parametric equation equal for ship A equal to the x parametric equation for ship B, and do the same for the y's.
Tracy Upper from the main office, Tracy Upper.
So for the x parametric equations, I'm going to have 6 minus 6t, and that equals negative 14 plus 17. Okay, I want to solve this equation for t, so I'm going to get 20 is equal to 13t. So t is equal to 20 13ths of a minute. So now what I want to do is I want to set up the same equation, except for using the y coordinates. And I want to solve for t and see if I get the same t that I did for the x coordinates. So for the y coordinates, I'm going to have 10 minus 8t, and that's equal to 6 minus 3t. Again, I'm going to solve for t. So I'm going to have 4 equals 5t, or t equals 4/5 of a minute. All right, so I can see that I have 2 different values of time. This system is inconsistent. That means that even though these ships' paths are going to cross, the ships are not going to be in the same place when they do. So because this time is not equal to this time, there's going to